Now we have started electric potential. And yesterday we made some progress. We made an analogy between electrical potential energy and gravitational potential energy. And then we used electric potential energy to define electric potential. And then we did it for a constant field. We did it for a point charge. So there's a couple of things to review here. Electric potential. Electric potential is different than electric potential energy. For a constant field, like between capacitor plates, we said that E is equal to, the symbol for potential is, well, in general, I think, start with that first. Potential energy in general is defined as, the symbol for potential is V, capital V. And I usually just put it a large V with no hats. When I put a hat, it means voltage, or means volume. But the kind of lay term, electric potential and voltage are the same thing. And the units for electric potential is the volt. Do it like that. So the general definition of voltage, and it's usually defined in terms of, it doesn't really make sense to talk about voltage at a point. Rather, it makes more sense to talk about the difference in voltage between 2 points. Same as energy, potential energy. It's really the change in potential energy that we're concerned with. So all throughout the book, we describe the symbol is a delta V. And so when we define it, delta V is defined as, the change in electric potential is defined as the change in electric potential energy per unit charge. And so that's what voltage is. Whereas potential, the change, potential energy, or the change in potential energy means the same with regard to electrical energy as it does gravitational energy. Electrical potential, or voltage, is the change in electrical potential energy per unit charge. I also talked about the fact that there is a gravitational potential energy that we did not define last semester, but it does exist. And so even in that regard, there's an analogy between the electrostatics and gravitation, from gravitational principles. Now, as I was about to say a moment ago, that's the general definition, but we can now look at a constant field. And for a constant field, which I derived, the potential energy and also the potential between 2 capacitor plates. E basically UE, excuse me, and delta UE is equal to Q naught E times delta X. And of course, then for that particular example, delta V then is just going to be equal to E times delta X. And in general, we can say that, and I guess I should put in, there's a negative sign here. I'll do the absolute value. But in general, delta V is equal to the negative of the integral of E dot dx. All those. Well, this is for a constant field here. These two. A bit specific. This is in general. More specific. In general, the relationship between electric potential and the field is negative of the integral E. And finally, we derived the electric potential energy and the electric potential for a point charge. Now, a constant field, yeah, well, I'll draw the picture, but we did it yesterday. You can take out some notes from yesterday, from Monday. And for a point charge, so the potential energy, electric potential energy, so the potential energy is defined as K. So you have to think about it in terms of the potential energy between 2 point charges. So the way we derived it for a point charge within another external electric field. So the way we talked about it is that you had a large charge or some charge distribution. In my case, I think I just used external charge. So I think I called it Q, so Q negative. And it has a specific field associated with it. That field is going to be attractive. Well, field that points radially inward toward the negative charge if it's negative. And you might have a point charge, a test charge, somewhere in the vicinity of that field. So like here. And let's make it test charge is always positive. Now it's so small, again, the properties of a test charge is small enough that the field is negligible compared to the external field. It's a positive charge, and so at a distance r away from that, and we had discussed the whole concept of bringing the test charge in from infinity. You have to go back and look at that lecture. So when we define gravitational potential energy here, we define it in terms of the energy in the system being both the charges. And so we can write down the electric potential energy, let's say gravitational and electric, as UE equals K sub E Q negative Q plus over R. It's a scalar quantity, has units of joules, so we don't write it as a vector. In fact, talked about the properties as well yesterday. Obviously, if electric potential energy is a scalar, then potential is a scalar as well. It is. So that's the energy. But the potential, actually, Q naught, inconsistent with this symbol terminology on the other side of it. And we can see that it's positive. We know it's defined to be positive anyway. That's charge. And so, of course, understanding this general definition, we take this and put it in here, we're dividing by Q naught. So that gives us the definition of electric potential for a point charge. Which is equal to, and again, we really are talking about a change in potential, but with regard to spherical bodies, a change in potential, the zero potential energy point is at infinity. So you could write it as a delta E, but that means, you're always bringing the charge from infinity to some distance R away from the charge setting up the field. So when you consider the delta quantity, final minus initial, that's going to be U at position R minus U at infinity. But U at infinity is always defined to be zero. So that's why we just really speak in terms of, it's not really talking about the potential energy at a point. Even when you write it like this, right? It's really talking about the change in potential, but you're always measuring the original potential to be zero at infinity, and you're always talking about the difference that it took to bring the charge from infinity into this point. So that's implicit, both potential energy and for potential. So you just have to keep that in mind. Not really describing the energy at a point. It's same thing here. Goes to delta P at position. And as I said, putting that into this equation, you just need K sub B Q minus overall. So in both of these cases, you see, well, in this particular case for potential, you see that even though we're talking, we're still talking about, that would be the potential that this charge Q naught would have at position R. But the interesting thing is that whereas electrical potential energy is talking about the energy between the two charges, electric potential, when you divide out Q naught, basically it's saying that this electric potential has nothing to do with that charge. That value of potential is that value at that point in space where the charge just happens to be, because you see Q naught is not associated with the formula for electric potential at all. So whereas electrical potential energy is about the system comprised of both the charge setting up the field and the test charge, electric potential is really just about the space surrounding the charge setting up the field. Same thing with the idea of the field, right? The electric field, AQO, we said the same thing about that, essentially, that this field, E, it's here in this space, whether there's other charges there or not. Potential, same thing, it's in that space as long as there's a field there, whether other charges are there or not. Force, well, no, you have to actually have that actually have to have a charge there for it to be forced upon, but an electric potential, a electric field, nothing has to be there. But for force and for energy, yes, something does have to be there. Okay. So that was the entire lecture. It took a whole lecture to discuss all of that yesterday. Kind of a lot there, and it's a little bit different simply because you need to go back over that. Simply because the concept of a potential is new. That's not something that we've discussed before in mechanics, even though there are analogies in mechanics to this. Just for conventional reasons, we don't really work with problems where we need to do that. In the sophomore level physics and mechanics. So all of that we discussed yesterday. So we'll definitely go back and take a look at those lectures. Yes, that's basically it. Other than working problems, some more problems with this equation here. So it's a medical problem. So I have a definition here at this point. We use to define the concept of electron, EV. I'm not saying we've already defined electron. I mean, concept of an electron volt, although I don't feel like I'm saying that right. So now I'm having a brain fart. EV. Wow. Electrovolt? So let me, I don't have that qualitative term written down in my notes. I just have it mathematically. So look this up. Oh, maybe that is right. Electron volt. Somehow that just feels off. Yeah, electron volt. It sounds weird for some reason this morning. So an electron volt. This is kind of like it's kind of like when people say, at least I make the analogy that when people talk about G forces, it's kind of the same thing, where you're comparing acceleration due to gravity to weight, just for an intuitive comparison. An acceleration and a force are not the same thing, right? So, but because weight is a constant multiple of, a constant multiple of acceleration due to gravity, excuse me, and because people don't necessarily have an intuition for mass, right? If I tell you how much is 50 pounds or 50 newtons, you might not have any idea. Sorry. If I tell you, how much can you estimate how much 80 kilograms is, you might not have any idea. But if I ask you, can you gauge intuitively does 180 pounds, 175 pounds, can you gauge how much that is? You probably would be able to do that. But in fact, the person who weighs 75 pounds is approximately 80 kilograms. Like that's my way. I'm a little bit less than that, but about 175 pounds. I'm a little bit less than 80 kilograms. So that's actually 800 newtons. So 175, well, 175 pounds is approximately 800 newtons. So, but when we talk about pilots in an aircraft experiencing um, G forces, what we mean, and we say that so the weight is 10 G's. Well, again, 10 G is not a weight; it's an acceleration. But what we mean is that the force on that person is 10 times his weight of, 10 times his normal weight, which is the same as saying 10 times the force of the earth on that person. So it's just a way of speaking that allows us to use our intuition to make a more quick comparison that we understand. Electron volt, it's kind of the same idea, where uh, electron, we talk about it in terms of, we define it in terms of charge. Well, we can define it in terms of mass and charge, but in this particular case, we define it in terms of its charge. We know that the elemental unit of charge exists on both protons and electrons, and that elemental unit of charge has the value 1.601 times 10 to the negative 19 coulombs. So when we say electron volt, we are comparing the charge on a electron to the amount of energy, electrical energy that charge has. So again, charge and energy are completely different concepts in the same way that mass and weight are. But because the energy, if you look at this definition here, the energy of the electron, or energy in general, is going to just be equal to the charge times the voltage of a particular, of some system with of the electrical energy of a particular system. In other words, I could write this as delta U in general is equal to Q times delta V. In units, this has a comparison that joules, joules are equal to coulombs times volt. So when you're so in order to determine the amount of energy associated, electrical potential energy associated with an electron, you just simply multiply the charge, the value of the charge E times the potential, I guess, associated with. It's kind of like this: if you had a point charge, the electric potential at a point, a distance away from that charge is going to be I'm not saying that quite right. Actually, let me say that a little bit differently. Qualitatively, what it means is that there's some very specific language that's used to define electron volt. So I want to use that language and I forgot what it is. So let me do that as I write down this definition. I don't have it that way in my notes. It's the amount of energy Remember. To move an electron through 1 meter of, you know what, I'll look it up. Amount of energy required. Yeah. It's the amount. Okay, what's happening here? It is the amount of energy. Well, you can say it two ways. It's the amount of potential energy required to accelerate an electron through 1 meter. Yeah. Um, electron volt, or EV for short, abbreviation, is the amount of energy of electrical or electric, either one is fine, electrical or electric potential energy required to accelerate an electron through from rest to electron from rest amount of electric potential energy required to accelerate an electron from rest through an electric potential difference of 1 volt in a vacuum. And um, yeah, and so then by definition, that amount of energy is equal to 1 EV. And so using this general definition, we can say that 1 electron volt then is defined as E 1.6 times 10 to the negative 19 coulombs times I'll just write it as a symbol, E times 1.0 volts. Now, another way to say that, because in a vacuum, there's nothing to take the energy away from the, nothing to dissipate the energy while that's happening. And so all of that electric potential energy then required to do that will then manifest within the particle as kinetic energy after that's done. So a lot of times you see the definition written in terms of kinetic energy. I like to do it in terms of potential energy because I know it comes from ultimately this definition here. So you might see it stated differently that it's the amount of kinetic energy obtained by an electron volt. Sorry, the amount of electric energy obtained by an electron as it is accelerated through a potential difference of 1 volt. But because of conservation of energy, basically the amount of kinetic energy that it obtains as it does that must be equal to the electric potential energy that was associated with that electric field, because that caused that electron to do that. So I like to state it this way. Okay, yeah. So yeah, electron volt. Okay. So that said, one of the reasons that we like to work with electric potential, and again, this is kind of a one-dimensional version of this relationship, but in general, we can write a more general relationship for this expression that I have here for equation 4. And that expression is the following. In other words, we used it to derive the equation for a point charge, actually. And these are very specific examples, but in general, we could write this as a kind of a three-dimensional relationship, and that's what we used to derive basically these guys. And I guess I'll put that here. Equation 9, that we can say that potential in three dimensions, it looks more like, well, we know that the electric field, let me just write that down again. Well, we can say that it's equal to minus integral E of R dot dr. But for a point charge, we've already determined a couple of weeks ago that E is equal to K to V Q over R hat. So if we take this guy and put it into here, this is what we're talking about. Negative integral K to E Q R hat. And of course, dr has the units of dr R hat. They're always going to be parallel or anti-parallel, depending on whether you're talking about a positive charge or a negative charge, right? dr always points radially away from the charge. I shouldn't erase that, but dr points radially away. Now, for a positive field, the electric field also points radially away, but for a negative charge, positive charge, for a negative charge, as I just erased, the electric field points in. So for a negative charge, R and dr are dr and r are dr and E are 180 degrees relative to one another. For a positive charge, they're 0 degrees. But the point is that negative sign arises formulaically because we have negative charges, and we have to account for that. So but the point is, when you do that dot product, you're either going to get 180 or 0, or cosine of 180 or cosine of 0. So they will always be along the same coordinate direction, which is r. So we can write this as a scalar quantity. I mean, it is a scalar quantity, but we don't have to write it as a vector one. We can just say that, for a point charge, we have minus in a case of B. Integral of U over R dr. I'm just questioning, when I take the dot product, does that sign go away? It might actually. I think it has to go away whenever I take the dot product. Because if it's a negative sign, then I get 3. If it's a negative charge, I get 3 negative signs. That's formulaic. This would be negative, and then this would be cosine of A, which would be negative. So if it's a positive charge, then it's negative. It's positive. It's still negative. So here, positive charge and negative. Negative charge. Oh, but that's two. Yeah. So the negative charge is 180. No, I guess yeah. No, I keep it. I think you keep it. We keep the numbers, so we're good. Yeah. Um. Yeah. Actually, it should have been R squared. So that should be R squared. Oh, yeah. Yeah, that's right. Mm, okay, I'm gonna have to check that. Inconsistency in those before the interview or taking the interview. Is that R squared or not? No, it's not. So I'm having a great day this morning. There's a lapse in my notes. I need to definitely put things in. Yeah. I can figure that was what's going on here. Yeah, I think it's a matter of definition here. When we write this equation, we write it in terms of charge, the differential in terms of charge, not in terms of coordinate. So I really need to write it in terms of dq and not dr. And yeah, I think that's he'll actually rather we just write it down, but potential to start with. So I kind of screwed up here. I'm gonna take out this. Not really a derivation; it's a definition. So I can't sensibly get from what I wrote to. At least I don't think I can. We defined the potential just comes out of defining the potential energy, and so yesterday I went as far as defining the potential between for a point charge, and that was that V was equal to. Actually, we can do a couple of things. Let's do it in terms of energy and potential. So these are all definitions. We define the electric potential energy as K between two charges as Q naught over R. But then using the general definition of potential energy, the potential for that then was equal to K Q over R. We can do that for a system of charges. So like if we have some test charge, but we have various charges Q in a vicinity, then U is going to be equal to A to B Q naught times the summation of various charges. I guess out. So I'm just going to use conventional notation. I'm going to go back to just using small q, but that just means it's the charge setting up the field, and Q naught is always associated with the test charge, Q and Q naught. So this energy then is going to be all the various charges Q sub I over the R sub i's. Whereas the potential, same thing for a series of charges, the potential then is going to be equal to K sub B times Q naught times the summation of the Q sub i's over the R sub i's. And then for a continuous charge distribution, the potential energy is going to be equal to K sub B times Q naught times the integral of the differential charge element associated with that continuous charge distribution over R, where R is a variable. So these things are just defined to be so. There's nothing that we actually derive to get to them. This is what I was trying to do for a point charge, and that's not the way it's done. So dq over, sorry. No. This is out. Q is out. Let's just base B summation of Q sub I, R sub I, A sub E, Q, A sub E, integral of dq over R. Okay, so what I really want to do today is to focus on this guy, these. Now, once we have the potential, we can just multiply it by a charge that's at the point where that potential exists, the test charge, and we have the potential energy. So in general, we don't really calculate potential energy. We focus on calculating potential because once we have this, we just multiply this thing by Q, not by the test charge, and we have the energy associated with that charge in that system. So I want to do a couple of classic problems where we calculate the electric potential for continuous charge distributions. Basically, some of the same types of distributions we did for the field. So, we did like a ring of charge and a disk of charge, those things. And what I was trying to lead up to is the reason that one of the significant things about the electric potential is that ultimately what we want to know, as I talked about in previous sections, we want to know the energy or the field of what the electric field looks like in a region of space. And we've looked at several methods of doing that. We used Coulomb's law where we calculated it directly. But then in the last chapter, we used something called Gauss's law, which gave us a little bit easier way of calculating it using symmetry. But we can also calculate the field from the potential. So if we have the potential, we can get the field, and sometimes it's easier to get the potential from an integral point of view than it is to get the field directly from Coulomb's law from the integral point of view. That is to say, for point charges, the definition was, what do we say, a delta V. Like when we define potential, we said that delta V, right, is equal to delta U over Q naught. But if we have a continuous charge distribution and we're dealing with differential charge elements, then these voltages go to the difference in the voltage and they go to differential changes in voltage and differential changes in potential energy. So well, I guess really I should say we should actually not look at it from that point of view, but look at it from this point of view. That as I said, the relationship between the field and the potential is the following, that that a differential voltage is equal to the negative of the integral of the other is equal to the negative of E dotted into dx. But you take the absolute value, you do the dot product, what you have is dV equals minus or equals E dx. So from a differential point of view, you can write the electric field as write these numbers. E is equal to the absolute value of E. It can be is equal to dv dx, right? It's just the differential form of the relationship. The integral form, as I had written down earlier, if I take the integral of both sides, I have that integral equation. But if I can write a differential form of the equation in this way. So the point is that if I can figure out the potential, the formula for the potential in a region of space, and then I take the derivative of that formula, that can give me the electric field. And that can be easier than calculating sometimes the electric field from, from Coulomb's law directly. And again, we said we could use Gauss's law, but we can only use Gauss's law in situations of high symmetry. And we might not be able to practically set up. We might not have high symmetry well, oftentimes we won't. This is the exception. The problems that we did last week, that's why there are only a few of them that we did, because generally you won't have, high symmetry like that out in space. So you can use this formula to calculate the potential because it's easier than Coulomb's law. And why is that? It's basically almost looks like Coulomb's law, but without the R. It doesn't have the 1 over R squared, it has the 1 over R. So it's oftentimes easier to integrate a system, mathematically 1 over R than it is 1 over R squared. So we can take the potential and the equation, the brute force equation for potential, and determine the potential directly. And then once we have that potential, we can take the derivative of that formula, that result, to get the electric field. And it sounds like a lot of work. Sometimes it is, but still it can be easier with a lot of charge distributions to do that, as opposed to calculating the electric field directly from Coulomb's law in cases where we don't have high symmetry and we cannot use Gauss's law. So it's a thing. It's something that we do. So what I want to do is to calculate the electric potential for, what do I have here? A ring of charge, and then a disk of charge. And so we did that last week, as we found the electric field for a ring, or as 2 weeks ago, for a ring and for a disk. And so using Coulomb's law. So we can do it here, and then could take the derivative of that and compare that to electric field that we got last week, or whenever we did it. Okay. So our ring of charge, determine the potential at points along the axis of a uniformly charged thin circular ring of radius A and total charge Q. So here, I guess I did it in terms of total charge, not charge density. Yeah. Let's go ahead and place this so that it's, and I think the orientation we had previously, where the ring is in the Z plane. So it's the x to z plane. So it might look something like this. And so my point P is here along the y-axis, and we've centered the charge distribution at the origin. So this is point P, and we want to determine that. So the problem would be find the potential, electric potential at a point along the bisector of a ring of charge Q and radius A. So here's my radius A, and the charge is charge Q. I could have done it in terms of charge density, but the total charge on the ring, just 2Q, whatever, it doesn't matter, because we know the relationship between charge density and charge. For this would be Q is equal to whatever the charge density is, charge density would be lambda, because it's linear charge density times the circumference, which is 2 pi times A. So you could go back and forth. Q is equal to lambda 2 pi A, lambda is equal to Q over 2 pi A. Now, before when we were doing problems like this, I would do something like draw. You still want to think of breaking the charge up into differential charge elements. So in this case, the differential charge elements would be, like very small arc lengths, like that. And you want to contribute, think about the contribution of one of those at this point. So let's say we do the ones right up here at the top. So say there's one little element right there, and I'm going to, to color it in just to emphasize it. You know how we would do, we would figure out what is the potential due to that element at this point using symmetry and geometry and that sort of thing. But unlike the field, I'm not going to draw a vector down here. Like I'm just going to draw lines that represent the geometry, but there's no line that's going to represent a vector representing a field, because it's not a field, it's a scalar quantity. So keep that in mind. That's the difference here. So like here, it's the potential at that point due to that charge element. So the geometry then, so I'm at radius, this distance here is A. Like if I looked at a right triangle associated with that, if I assume that this is position Y right here, then, it's an arbitrary point Y. But if I looked at a right triangle associated with the geometry of that situation, it's going to look like something like this, like, so this is point P. This distance is Y, this distance is A, and basically my R, which would be the distance from the differential element to
the field point, R is going to be equal to a squared plus y squared, or R squared is equal to that. R is equal to the square root. So we're going to put that in. R then is equal to the square root of a squared plus y squared. And if we want to find the potential, again, we use a formula that I gave you. VR, or V of R, is equal to the case of B times the integral of dq over R. That's the integral that we have to work out. So if the whole thing is Q, then this little element, that charge is just dq here. In fact, I should put this, we have this pointing somewhere else. The charge of the whole thing, but that little charge is dq. And dq, of course, is going to be equal to, I guess you would call it lambda dq is equal to lambda 2 pi. And that arc length, if the whole thing, yeah, I don't know, how would you do that? Oh, yeah, you have to use the, 2 pi times the radius. So, yeah, it's just that little distance right there. So that would be like a ds, I guess. Yeah, let's do this over here. Let's now bring it back. So this dq is the dq that's on this little element here. And that little element is just over a ds. Yeah, so I guess we could just write it like that. So dq is going to be equal to lambda times that differential arc length, which I'll call ds. Yeah. And yeah. Right. So 2, 3, 4. Yeah, so dq equals lambda times. So even though I don't know what lambda is, I didn't write this in terms of lambda. You still have to use lambda. And it's still convenient to use lambda. You don't have to, but it's still convenient to use lambda. When you're working out the problem. So we can then substitute equation 2 and equation 4 into equation 3. And what I'll have is that, so 4 and 2 into 3. And that will give me the potential at point P, CRP, equals K sub B, the integral of lambda ds over a squared plus y squared to the 1/2. Yeah, it's going to look like a trivial integral, actually. Yeah. It is trivial. But it's just what it happens. It just shows you how much easier potential is than charge, than field. All this stuff is really constant except for ds, right? So a is constant, y is constant, lambda is constant, it comes out of the integral. And so vp is equal to k sub b lambda over a squared plus y squared to the 1/2 times the integral of ds. And basically, ds goes all the way around. It goes from, I guess what you have to do is, technically, you would break that up into an r d theta. Yeah. If you really wanted to be correct. So, you know, if S is equal to r theta, then ds if S arc length is equal to r theta, then ds is equal to, basically in this case, a, or it's r d theta. Right? So in my case, that's going to be ds is going to be equal to a times d theta. So if you put that in, you just do the integral right here, then plug it in. So ds, integral of ds is equal to integral of a d theta, where d theta goes from 0 to 2 pi. A is a constant, so that just becomes integral of ds is equal to a times 2 pi, or 2 pi a. So then this final solution then is that the potential, putting that back in there, the potential at P is equal to K sub B lambda 2 pi times A over A squared plus Y squared to the 1/2, and lambda 2 pi A is the total charge, Q. So the potential at that point becomes K sub B Q over A squared plus Y squared to the 1/2. I made it more than what it, I just wanted to put all the steps in there, but you could have done this in 3 steps, right? I didn't really even have to break DQ up into lambda ds, but I just wanted to be very clear. Do me a favor, let's do the limiting cases. So first of all, it's who's Bron, how you doing? Bron. So if I get that's the same thing we did with the field. Yeah. If I get very far away from this charge distribution, what do you think it looks like? Like if I'm, way far away, what does the thing start to look like? What type of charge distribution? Yeah, lambda is involved. That's right. That's what continuous charge distribution means. No, it's not linear. So I'm asking 2 things. I'm physically asking if I get very far away. So this is a ring, right? It's a ring of charge. If I literally walk very far away from that ring, like literally if I had a ring, like a ring of finger ring, you can see it if you're very close up, this ring has a hole in it. But if you're a football field away, what does it begin to look like? If P gets far away, yes. Yeah, point charge, wonderful. Yes. So if that's the case, then the field should start to look like the field of a point charge. So I want you all as a class to apply the limiting case to equation 13, 11, 12, and prove that this solution should reduce the solution of a point charge under the circumstance where I guess this is where Y is much, much larger than A. Do that right now. The limiting case. yeah. Well, it doesn't really go to, yeah, y goes to infinity. Yeah, that's right. Out point charge gets very, very small. Yeah, y goes to infinity, but yeah, it doesn't have, yeah. Even it doesn't, it goes to zero before it goes to infinity under certain circumstances. So you don't really have to take it to infinity, but it's going to look something like this. We do that situation where we say, we factor out a y. So it'd be something like, the limit of v sub p is, so you have k, q, and then in this thing, it's going to be 1 over quantity y squared times a squared over y squared plus 1 to the 1/2. Well, all of that to the 1/2. I basically divide through by y, divide out a y, or factor out a y. Now, when I take a y out, I'm going to get k, q, and then I'll have a y times a squared to the y squared plus 1/2. Yeah, and in the limit as y gets much, much larger than a, this term should go to 0 before y even gets to infinity, really. So what you'll then end up having is, in the limit as y is much, much larger than a, v of p, we get k, q, and this thing goes to 0, and then you just have over y. So it starts to look like the electric field that we just calculated. Sorry, the potential that we just calculated for the point charge. In the other direction, the limit as a gets larger than y, I kind of just did it in my head right now, and you get something that's like a constant. And that's, I think mathematically, when you're at the center, the very center, the potential should be 0, because clearly stuff is going to cancel out. It should all cancel out, right? Because of the symmetry. But if you're just an infinitesimally distance away from the center, what I'm getting is a constant whenever you do it in terms of charge density, which it probably makes sense. It's hard to visualize that, but so what that probably means is once you come off the center, the potential doesn't change much within a certain region if that, whenever you're within a limit below a critical value, in the limit where that distance away from the center is much smaller than A, then the potential doesn't change that much, I guess. But that distance would have to be, it's, people don't do that problem much. But it's not linear though. Potential has never been linear, Braun, for the potential. The field, on the other hand, would be. That's a nice one. We did that problem, and we saw that it became linear inside there. I think, but those are different problems, but not for this potential. It would never be linear, I don't believe. Cool. Let's do a disk. See if you can do it. And it's a situation where we use that solution as the differential element for the disk. But 20 minutes, yeah, we can finish up on that. That's a nice little problem to do. And it's probably one that you probably see in your book. They probably have an example in there of this and Halliday and Resnick. I'm going to, a lot of that geometry we can kind of keep. So I'm going to just erase this stuff. And we can reimagine the same picture with the same orientation. Oh, well, let's keep that solution. We did something similar when we did the electric field. I did the electric field of a ring, then we did a disk, but we used the solution of the ring as the differential element for the disk. Same thing here, but I think before we had to use. I ended up figuring out that integral. No, that was something else. That was for that was last week where I did the drag, but I guess it was a week before. I don't remember. It might have been Monday of last week where we can't remember where we worked out. No, it was before, a couple weeks before we did the electric field of a disk. But so here, let's do this. Let's make let me use a different color. Maybe purple. Now, erase this. What we now have is a disk. Okay, you've got a disk, and maybe I could do something like that. It's a disk. It's getting a little messy. But this ring now is like, it's the differential element, where I've taken the ring and I'm going to look at the potential of rings. Give it a little bit of thickness there. A little thicker. Take that away. Now that whole thing is DQ. DQ is now this thing. So that is at position R, and it has a thickness dr. So that's not a constant. It's not a. So the radius of the thing is still A, but that particular ring is at position R, and it has thickness dr. So now it has an area to it. And the total radius of this thing is still A. So, but that goes all the way out to here. So R will go from 0 to A, basically. So find the electric potential point along the bisector of a disk of charge Q and radius A. Again, we actually could do this as a double integral using the same differential element that I did, but then you have to integrate both. Here, integrating with the ring, I can convert it to an integral over a single variable, where I'm using this whole thing, ring, as the differential element. But you got to kind of rework a couple things, like, so dq is now going to be, you have to use sigma dA, where A is the area of the ring, right? So, and then I'll let you try to finish it up. So dq now becomes, so this R is still the same, that doesn't change, but dq becomes the charge density on that thickness times the area of that thickness. So sigma times dA. I use a small d area. D, yeah. And the area is the circumference times that radius. Times the circumference sorry, the circumference times the thickness. So dA, you just have to, that's not really physics, it's just mathematical logic where I'm getting, you work out the dq in the area. That's always, so sigma, the area then, no, dA, dA has to have units of meter squared. So you get the one, basically you take a ring, which is length, we just had, so 2 pi times r, that's not an area, that's a length, right? But then I add another dimension to that, and that dimension is thickness. So then that thickness is dr, which also has units of meters, so that becomes meter squared. So that's one way to describe the area of that. It's kind of like a frisbee or something, like a ring. So then dq, so if I stick 4 into 3, dq is equal to sigma times 2 pi r dr. And r will go from 0 to a. And so now we use sigma to convert, because otherwise we would have to take theta, also, which would give us a double integral because it's an area. But this way, we imply that the area is, we've taken the area of that whole thing because the 2 pi r, the radius in there implied, and so we've converted a double integral to an integral of the single variable, the variable being r in this case. Now, that's just the geometry and the math, but now you have to kind of put that into doing the potential. So go ahead and find the potential. And we're still, the formula would look basically the same, but now it's a two-dimensional problem. So V at point P is still going to be equal to, formulaically, case V integral of dq over r, but now the dq has changed. So go ahead and work on that for a few minutes, see if you can finish up and get that final solution. And that will be it. That will be the chapter. That'll be the end of the next chapter. So go ahead and do that. Yeah, so this is the chapter on electric potential, chapter 24. I'm gonna push this along because I want to say some things and kind of talk about a few things before we finish. We've got 15 minutes left. Get y'all back up here. Let's sit down for a minute too. Oh, oh man. Let's knock this out. So again, when we substitute in 2 and it's all these, 2 through 4, 5 into 6, then we get this kind of integration. We get so B sub P, V of P is equal to K sub B, and we're going to get sigma 2 pi r dr over that A becomes, this becomes R now. Well, yeah, so now what I use, I'd call this R. That thing is a constant. Let's call it distance that I'm away. And that's always a constant too, because, so let's call it rho or something. I don't know, so let's make that rho. Yeah. So I don't know. And so we keep R the integration variable. So when I plug that in, so this is like over rho really. So we can, oh, you know what we could do? Yeah, let's call it not rho, let's call it capital R. I don't know why, but just, yeah, so capital R. Like that symbol better, capital R. Because it's constant, actually, it doesn't change as we go around or as the integrals. Oh, actually, that will change. So that will change now. It does because it goes up and down, so that does change. Oh, maybe it should be the other way around. I want to keep that as an R. It's so more classic. So we could call this thing, maybe this becomes rho. So that, we could make that rho. So that'll be a variable. Like a rho as in, sometimes people use, for cylindrical coordinates, they use rho. So it's like a cylindrical coordinate. So everywhere up here, this is all these are rhos. Rho, d rho, rho, rho. Yeah. And this is a rho. That's a rho. So that now, that's the integral of square root of rho squared plus y squared. Yeah. Now, with this integral, it becomes u substitution. Look at this. So all the constants come out. And so you have k sub b. So k sub e sigma 2 pi times integral of rho d rho over square root of rho squared plus y squared. So that's just, you can accomplish that with u substitution, which is easy. So U becomes rho squared plus A squared, and du becomes 2 rho d rho. And when you integrate, so then you integrate, and you will get, go ahead and put the K sub B in. So Vp is equal to 1 over 4 pi epsilon naught times sigma 2 pi, and then times rho squared plus A squared, where rho goes from 0 to A, 0 to I have to change up the symbols here. Oh, that's right. That's Y. That's not A. That's a Y in there. Sorry. That Y doesn't change. That's Y is outside. So yeah, it goes from 0 to A. So pi goes 2, and then leaves a 2 down here. So we get, in the end, our final solution is going to be Vp. So outside, we will have sigma over 2 epsilon naught. And then when we put in the limits, we're going to get the square root of A squared plus Y squared minus, I guess, the square root of Y, which is just with the square root of Y squared, which is just Y. I'm going to leave it, yeah, minus Y. And, you know, we could put it in terms of charge, but I'm going to leave it in terms of charge density. So you might actually see this problem worked out in your book. So that's the final solution. It's a classic result, physics for a disk. So we can compare the ring, the final resolution of the ring, to the disk. You see it's time. What was that, Rick? Torres, what was that? 23? What is chapter? No, I think this chapter is 20. I'm looking at the digital text. It's chapter 23 is Gauss's law. So we finished that last week. This is the next chapter, chapter 24, electric potential. So now we finished this. Oh. All right. They've said a little bit more about a constant field, electric potential there. Yeah, I'll just write that. I think I already said that, but I'll just do it here. So there is a relationship between potential and a constant field. This is all point charge. I wanted to work that out, but I did this before, I think. But delta V, you know, V delta V is equal to, for a capacitor, is equal to Q times E. And that's V final minus V naught. Usually we make the V naught 0, so basically Q times E. So in general, that's the case. Yeah, I guess let me just, in general, for a constant field, delta V is equal to negative, actually, QE. Its magnitude is Q, is positive. And whenever the E is not constant, it becomes the integral, that delta V is equal to the negative the integral of what am I doing? Oh, there's no Q there. So, no, it's equal to E times delta X, my bad. So that whenever you, for a non-constant field is E times E dot dx, or dl, sorry. So they might work out a little problem like that, but that basically is the end of the chapter. Oh, okay, 2 minutes. So yeah, I just wanted to kind of check in with you on the voting day. So vote, I voted this weekend, you know, it's kind of coming down to the wire. Looking at the news this morning, and there's just more drama and craziness. This reminds me very much of the history of the time when people were burning books, like in the Middle Ages. This idea, you know, you're all a scientist. I know I preach this all the time, but it's important, you know, we kind of have something every week leading up to the election. But just go out and vote. You're scientists. You're going to be scientists. Believe in science. Today, the executive branch was verbally berating Dr. Fauci. Dr. Fauci is amazing. Those people are so good. I mean, I think I'm a pretty good professor, and I've only been teaching for 25 years. Dr. Fauci, literally the position that he has now, I was a sophomore in high school when that man, I remember when Reagan appointed him as the chief, whatever they call it, whatever his title is. He's been doing this for 40 years, over 40 years. So believe him when he says this stuff is real and what we need to do. And as we get more political, you know, you see these people, the leading scientists being disparaged. So don't believe it. Believe the scientists. That's what you want to be. That's what you're studying. Science works. Nothing's perfect, but you know, we know what we know based on trial and error and experience. And those people are, you know, they know what they know. So promote science. Believe in science. Stuff is not a hoax, right? So I wanted to say that, just to keep reiterating that, double down on that, and go vote. The other thing is, so they also talked this morning in the news cycles about the fatigue associated with what we're dealing with. There's a psychological and an emotional response to having to stay disciplined, and I can actually feel it, even in my teaching in the class, and I'm sure you're feeling it. But I want to encourage you to stay in there. I'm going to work with this. One reason I've been kind of not only, somewhat has been somewhat deliberate, somewhat is just because I'm tired as well. But, you know, with trying to get this management system up and acclimating the LMS, how it's affected our quizzing and homeworks and stuff. You know, I just made a conscious decision back at the beginning of the semester. It's just, I'm not going to be pushing. And you know, the lecture, the quality hasn't changed, but I know that it feels maybe the class is not as rigorous because I'm not doing homework every 2 weeks or whatever. I just want to, you know, I will be assigning, I know I keep saying that, but I got the stuff worked out finally for the LMS, and I know how to assign the homework. And so I will be doing that. But still, it probably won't be as much as what we normally would be under because it's just, things are much more stressful. And I don't want to, overwhelm you or, I don't think it's fair to have the course as rigorous in that regard is on the norm. It just isn't because, but we can still have very lively discussions here and do work through the class examples that I'm discussing you, and you will get, you don't have to work a bazillion problems in order to learn. That doesn't necessarily help you learn. But what we're doing in class and going through the intricacies of these different problems, that you're still getting the benefit of what you need to get in order to learn the material. So I'm going to start to put in the homeworks, and even though I'm going to go back and do homework even from the stuff we've missed, but it won't be as much as I would have given you if I had given it to you then or if we were under normal circumstances. Maybe 7 to 10 problems. I'm probably going to work some examples and maybe post those examples of problems I give so it can facilitate you moving through the faster pace. And that's how we'll handle that. And probably give a lot more time than I would have. So let's start this week, today, now that I've got that worked out. So just wanted to say that and just keep you encouraged. So keep reading the book, work through the probably examples, working through these notes, go back through the notes, work through the details of these notes, try to do it on your own without looking at the notes. There's a huge value in that, huge value. Yeah. So any questions, problems, troubles, or gripes before I let you go?
In terms of the homework, are we going to
Yes.
get assigned homework from chapter 13?
Yeah, I'm probably a little bit. And remember, like when the what the main thing I want about chapter 13, why I kind of put it there and keeps talking about it, is because in the class examples, every time we do a problem for graph for electric field or potential, whatever, we could do the same problem for gravity. So I don't know if they'll stress that much in the homework. I have to look specific at those homework problems, but I probably will give you a few homework problems from that chapter because I want to, I do want to emphasize gravity to some degree. So yeah, that's still a valid chapter.
Yeah, that makes sense.
Yeah. All right. Anything else?
I have a question for what edition of the book that was?
It's the digital text. So I think I don't know what edition it is. Let me see. And I showed you how to access the digital text, right?
I think it's the 11th edition of the book.
I think that sounds right.
Yeah, because I have the 14th edition, and that's why I was a bit confused about between chapter 24 and 23.
Oh, I see. Wow. They have which edition do you have, Rick?
For Sears, it's 14th edition.
Oh, it's not Sears we're using. That's not the official book anymore. That's now a supplementary book.
Okay.
Yeah, the book we're using is Halliday and Resnick, and it's the digital text. So it's the 11th edition of that book. You can still use Sears, but the homework problems, they're not even really coming from the book anymore. They're coming from the digital platform, but those problems do come from, kind of how Halliday and Resnick has introduced problems and introduced the material. So the Sears book is really now a supplementary text because that's not the one that Wiley uses, and I want to use the Wiley platform as the official management platform for the class. But it's still a great book to have, and in fact, when I was looking through a book just now, that was the Sears book, an older edition of that, 13th edition, I think. But so yeah, keep that in mind, Rick. Yeah, Babatunde.
I was going to ask, will you ever be open to going over questions from the adaptive problems or the practice problems that we might?
I'm always open for it. Always, yeah, always.
Okay, because I run into a few that I'm just going to figure out, but I don't want to take out of class time to discuss them. So, but if you are, I would like to maybe bring one up next time.
You can, or we can do it like, you can after class or just whenever we can set up a time. Usually Friday mornings are a time when but no one ever came. Remember, I was doing that in the summer.
Like
Yeah, we can.
Friday
Yeah,
morning from 8 to 10, I would do recitation, but nobody came, so I just stopped doing it. But that's also a good time to meet if you want to have problem solving or whatever.
yeah,
So
I'm
even
open
now,
to it. Definitely.
okay. Yeah, just let me know and we can work through those.
Will do.
All right. Anything else?
Are you gonna have like all the homework due at the same time, or is it gonna be
No.
like?
No, I'll spread it out. No, that's not gonna be at the same time. I'll give I'll have to figure out like how to kind of put it in. For the older stuff, like I'll probably have like a reasonable time period for the stuff we're doing now, but then for like previous chapters, you might. In fact, I was thinking about maybe, and I'm not sure which the cutoff will be. I think the Gauss's law and the electric potential, that stuff I want to assign homework for that this week, and maybe it'll be due next week. But the previous chapters, I might give you like 4 weeks or something. I don't know. I have to figure out what's fair. It might just be at your own pace too, and you can turn it in up until, maybe I give 4 weeks, and then you can turn it in as you need up until that point. It's self-graded, so as soon as you finish it, it's going to be graded. So maybe something like that is what I'm thinking.
And then is the homework like kind of like the practice where you select the right answer and then it's graded based on your accuracy, or is it?
Yeah, it's exactly probably like the adaptive practice. It's just you can't really see it, which is why I was having difficulty trying to figure out where it is. It's actually you can't see it until I assign it. But when you do it, the assignments are, so maybe I'll do 7 to 10 problems. I know something like that after I select them, because some of the homework, they're pretty long. It's like 24 and 23 problems, things like that. But I might not have to do all of them, particularly for the older chapters. But you have a certain time period where you have to get it done. And when that time period is over, or when you submit it, it will grade it all and give you the grade right there. So yeah, and it's multiple choice. So yeah, it's set up just like the adaptive practice if you've already started working through some of those, the same type of setup.
So in terms of this class, does that mean the homework part of the grade is graded based on accuracy of the homework?
Yes, it's whatever the homework grade is, the average of those is basically the average of the homework, and it's self-graded once you submit it.
Okay.
Yeah, but it's only, the homework is whatever I gave you on the syllabus. It's
I think you said like 15% or something.
for the homework.
Yeah, 15% on your syllabus.
What about the labs? I thought it was,
You made the homework 15% and then the tests 35%.
oh, okay, yeah, I did change it this semester. Yeah, because we have the quizzes in there now and all that. Yeah, so the the test of 35, homework is 15, and what else? What was the other thing? You're looking at it right now?
Everything else is like the same as like what you mentioned in the beginning of the semester, like discussions and quizzes are 5%, lab is 10, and the final exam is 30%.
Oh,
We're
why
like
did I
all the
do that?
same. There's just the one thing the thing you changed is like the homework and the tests. You had the percentages change a little bit.
Oh, I think I did that because, yeah, this summer I realized that the way we're doing it now, like previously, I just, before quarantine, I just checked the homework off. But now this is actually pretty rigorous, where you have to go through it. And so I felt like it was unfair because you have to do so much work with that homework, the way you have to get it right and all that, that's why I gave it a bit more percentage. And I thought it was substantially more work than doing the labs, even and the quizzes. The quizzes were easy the way I was making them. I think that was my philosophy on that, as opposed to the summer. Yeah, yeah. see. I think it'll, yeah. Okay, so yeah.
One more question. In terms of the labs, do you anticipate any more being assigned soon?
Yeah, I mean, we'll assign. Yeah, we will assign them from. But the reason that we haven't, I dropped off of that is because, again, these applications, I think they're kind of, well, Beyond Labs isn't new. It's probably like 5 years old. It's relatively new, but I don't think they completed building the thing. So
Yeah.
what I noticed in the electromagnetism lab, it jumps. So there was that lab early on in terms of motion of a particle, and then there's nothing on Gauss's law or potential or field, specifically on field. It jumps to circuits. So there's a whole gap that was missing. That's why we haven't done any labs. And the next lab, it picks up with circuits and resistors. So we have to kind of get, so that's why was an inconsistency there.
No problem.
And I'm getting familiar with it, just as it's new to me too. So, you know, I'm just trying to adapt and whatever. So that's why we haven't done a lab in a while.
Okay.
Yeah. Anything else? All right. Be safe, be well. And I will keep working, reading, and I will see you on Wednesday. And when on Wednesday, we're going to do the start the next chapter. So the next chapter is capacitors. So we'll do that, and I'll probably get through what I want to in pretty much a day in capacitors, and that'll get us into circuits. Okay. Oh, and discussions. Yeah, I hadn't done discussions in a couple of weeks because I had one is because of grading, because I hadn't graded the ones you already done, and also because I was anticipating assigning the homework, and I didn't know that, you know, it was kind of new stuff in the quizzes. I wanted to kind of focus on figuring out how to get that before I kept piling on the work with the discussions. But we'll come back to discussions. Supposed to be doing it every week, but a couple weeks we'll miss a few weeks. I wanted to get the homework and quizzes, get the protocol down before I get back to that. And I was just having difficulty working out how to do that the past couple of weeks. So that's why we didn't do the discussions. Yeah. All right. Anything else?
So based on what you're planning your schedule to be like, does that mean we might start circuits next week?
We will start, yeah. So I'll do capacitors on Wednesday. Yeah. So we will be into well, resistors is usually about 2 chapters. So, but what I do is I kind of break it up a little bit. We will do capacitors, and then at the end of that, we'll look at capacitive circuits. And then we'll do resistors. Capacitor is usually only 1 chapter, then for most books. And then resistors is 2 chapters. So the answer is yes, but we'll actually get into circuits for capacitors on Wednesday. We'll finish all that, then we'll go to resistors, and so the first Monday will be just presenting it, and then either by the end of the day on Monday, and certainly by Wednesday of next week, we'll be into resistor circuits. But then we have to put them together. So the answer is yes, we'll definitely be into circuits by next week, but for capacitors, we'll probably do capacitors in series in parallel, actually on Wednesday as well. We'll probably be able to get that in by the end of the day on Wednesday. Does that answer your question, Julie?
Yeah, that answers my question.
So definitely go ahead and start reading the next chapter of capacitors. You know, it would be helpful if you kind of read ahead, even as you do work through problems and examples and homework from Gauss's law and electric potential.